Okay. Hi everybody. um, I keep thinking about what Janina said. I don't know. The clock's not in the picture as that I can see, but I guess it's in the full video. I'm a bit late tonight, but hopefully I'll get home soon. I'm going to talk about structural change and go through a couple of these models just quickly and get them out so that you can look at them on Monday. And as I said in the lecture, you can either have substitution effects or income effects, and of course in general you're going to have both. But I'm going to go through a couple of really simple models where you just have either one or the other. Or they're totally dominating anyway, yeah. So here's the first model, and it's just got substitution effects. So what's the story? We've got two products, y1 and y2. And these are the production functions. Gamma L, KL, L, and gamma R, KR, R. So what have we got here? If we were going to draw a kind of circular flow diagram or a general equilibrium diagram, we'd have households, and we'd have, let's do it this way, we'd have two final good producers, and we'd have the resource sector. And there would be labor coming out of the households and going here and producing some good, and the resources coming out of here and helping to produce some good. Okay. So this flow is y1 and this one is y2. Yeah? And then how much comes out of here, that's y, isn't it? And y is a CES function of y1 and y2. I've just written y is f at y1 and y2 here. But actually here we've got something more specific. And then actually this isn't a full general equilibrium model. I don't think I specified the full general equilibrium here. I don't tell you where the resource or energy or whatever it is comes from. But you might imagine that some of this y goes here and some of it goes to the extraction sector. Would be one way of kind of closing the model. Okay, so we've got one output that's just based on labor and one that's purely based on the resource. And then to get the final good, you use both, or in a way what we can think of is actually these coming to consumers and then consumers getting their utility from combinations of the two. They want both because they're very different, these products. That's another way of thinking about it. But either way, we can say that aggregate production is alpha y1 to the minus epsilon plus 1 minus alpha y2 to the minus epsilon. I don't know why I made this minus. Whatever. To the minus 1 over epsilon. So if epsilon is positive, then there's not much substitutability between y1 and y2. If epsilon is negative, then they would be very good substitutes. If epsilon is 0, as I told you, it's actually Cobb-Douglas, although you need a bit of tricky math to prove that. Okay, and then we're told, let labor L and input prices WR and WL evolve exogenously and derive total energy use R. Okay. I'm going to pause there and think about how to do this. Okie doke. So what we can do is actually, even if we can think of this either as utility or as somebody sort of putting these goods together and selling them in combination to the household. And it's almost easier to do the latter, because then we could just think, okay, it kind of becomes the standard problem, because the person putting these goods together to get the combo Y is then got a profit maximization problem, which is just to maximize PYY, and we normalize PY to 1, minus W, I think I use W's, don't I? Yeah. W1, Y1, minus W2, Y2. Okay. Because remember, for this guy, the inputs are Y1 and Y2. So then, first order conditions, take the first order condition in Y1, what do we get? We get minus 1 over epsilon, square brackets to the minus 1 over epsilon minus 1, then we go inside and we have minus epsilon. So again, those cancel out, times y1 to the minus epsilon minus 1. So that's from this, and then we get minus w1 equals 0. So that's equals w1. Okie doke. So then we get, yeah, it's basically that. And the other first order condition, when we do in y2, this term is going to be exactly the same, isn't it? And then when we go inside, we get minus epsilon alpha y1. And here we should have minus epsilon, which is going to cancel with that, 1 minus alpha y2. To the minus epsilon minus 1 equals w2. So we've got those two equations, one for w1 and one for w2. But we can also work out W1 and W2 from the profit maximization problem of these guys. And if you want to, you could set that up. But it's kind of unnecessary, because actually, given perfect markets, there's really a very simple problem to solve here. Because Y2, how much do you make? It's just gamma R KR, which is just exogenously given, times R. What are your costs? So this is your production. What are your costs? Oh, well, let's do this one first. Gamma L KL. L is how much you make. Your costs are just WL L, aren't they? So what's the price of the good is the marginal cost of producing it given a perfect market. And the marginal cost, given these linear functions, the marginal cost is the same as the average cost, or the unit cost. So what's the unit cost of making Y1? It's the total cost, WLL, divided by the total quantity, gamma L KLL. So we end up with W1 is WLL over gamma L KLL. The L's go out and we get WL over gamma L KL. Okay. And W2, the price of Y2 is going to be WR over gamma R KR. Okay. So we've now got, if we divide this by this and this by this, we've got two equations for W1 over W2. We can eliminate W1 and W2 and get equations linking the wage and the price of the resource to a bunch of other stuff. So let's try that. Divide this by this, we have W1 over W2 equals something. This by this, we have the same. So here we have, these go out, and we have alpha over 1 minus alpha, y1 to this, y over y2 to this. We're going to turn that the other way up to get rid of the minus signs. y2 over y1 to the 1 plus epsilon. So I've switched it, and the minus signs have become plus signs. So that is equal to W1 over W2, which is equal to this over this, which is WL over WR, that over that, and then this is on the bottom line, and this is like bottom, which gets top, so it's gamma R KR over gamma L KL. You might need to do a couple of steps to get that clear in your head, but that's the equation. Okie doke. I'm a bit tired here. But we don't want these y2s and y1s, do we? We want to know, you're told to use these two equations. Okay. Derive R. We want to know big R. Okay. So far we've derived some equations which have these prices of the intermediates in. We obviously want to get rid of those because they're not that interesting. We're interested in the sort of outputs and inputs, the main. And we managed that, and we've got this equation. But then we come back to our original problem, and it's like, we want to know big R. But there's no sign of big R here, is there? But then we look here, and we've got y2 over y1. What's that? That's gamma R KR R over gamma L KL L. And I've done the stupid thing with little and big r's, where this is sort of firm level, and then the big one is aggregate level. But we're assuming symmetry, so little r and big R end up being the same thing. Okay, so we can write y2 over y1 as gamma R KR big R over gamma L KL big L. So we've got gamma R KR big R over gamma L KL big L. Okay. And then we have these brackets and stuff, but for now I'm going to take this, and then I'm taking 1 minus alpha over 1 minus alpha over. So then we have equals. Don't worry, I'm going to tidy this up in the end. Hopefully you'll see it. So 1 minus alpha over alpha. WL over WR. Gamma R. Gamma R. KR over gamma L. KL. Okay, so that's looking good, this side. But here we should have to the power of 1 plus epsilon. But why don't we raise everything to the power of 1 over 1 plus epsilon? Then this is as is, and this becomes like that. Okay. And then we see these gamma R KRs that we don't like, gamma L KL. So why don't we split this into two and say, like that. actually, it's not how I've done it there, but sorry, let me pause and decide what to do here. Okay, I'm going to carry on this way. So I've now written it like this, because then I'm going to take this gamma r kr over gamma l kl over. So then we have wiping that here, and we have gamma r kr over gamma l kl to this minus 1, which is minus 1 plus epsilon over 1 plus epsilon. 1 minus 1 minus epsilon. That is minus epsilon over 1 plus epsilon. Okie doke. So then we can actually take this back inside and put a minus epsilon on it, and we end up with the expression on the slide. Okay. So, what does this tell us? Oh, sorry, I need to wipe this. So how does R over L change if you change WR over WL? Well, it depends on epsilon, basically. I'm going to pause and... Okay, so it depends on epsilon. How much does R over L change when the relative prices change? So, let's make epsilon large, which means we're getting sort of close to some kind of Leontief story. Then we've got 1 over 1 plus epsilon. This is very small, which means that R over L hardly changes when the prices of the inputs change. It's Leontief. You're determined to have the inputs in a certain ratio, whatever they cost. Okay. So that's the extreme case of epsilon very large. Okay. What about epsilon 0, which gives you Cobb-Douglas here? The production function for this is a Cobb-Douglas of these two intermediate goods. Then, that's epsilon 0, then this is raised to the power 1, and this goes away. Then you just have that R over L is 1 minus alpha over alpha, WL over WR. And you end back up, if we bring these back over, you have WR over WLL is 1 minus alpha over alpha. That is the typical Cobb-Douglas result for a simple Cobb-Douglas production function, isn't it? Constant shares. WR over WLL is 1 minus alpha over alpha. So if we choose epsilon equals 0, which is quite a lot of substitutability between these goods, then we end up with a Cobb-Douglas aggregate production function, even though we've got these two goods, one of which uses pure labor and the other of which uses pure resource. And of course, when you look at the structure of this, it's obvious that this is going to happen, isn't it? Because it's almost as if you're just using labor inputs here and resource inputs. And then this, you don't really need this intermediate step, do you, with these very simple production functions. So, and then this is just Cobb-Douglas. We're kind of really back where we started. Okay. So this is like a super simple model that really, these intermediates, you could almost just leave them out. And yet then you're back where you started. Okay. But it's still an illustration. You could have models where, the production functions looked almost like this. So you had some goods which were very labor intensive and hardly used any resources, and other goods that were very resource intensive and hardly used any labor. And if there was plenty of substitution on the consumption side between those goods, then you would get the sort of Cobb-Douglas long-run aggregate function. You would get the behavior that we're after. Yeah. Okay, I think that's it. I'm just going to pause. Right, and one other thing, of course, if we go with Cobb-Douglas, then this term is 0 because it's raised to, it's 1, and it then disappears, which means that mucking around with these productivity terms, the k's here, which are productivity terms, is not going to help, because you've got 100% rebound. Okay, so if you make your energy intensive good much more energy efficient by raising kr, if you make it like 10% more energy efficient, basically you're going to reduce its price by 10%, and with this high degree of substitutability when epsilon 0, you raise the relative demand for it by 10%, and the demand for energy relative to labor stays the same. Okay. So that's the story there. Pause again. Yeah, and the last question was, what happens if we tax energy use? And I think let's have a quick look at that. Let me just think about that. Okay, so what would happen if we taxed energy use? How are we going to do that mathematically? Where is that going to kick in? Is it going to kick in the production functions? No, they're the same. No prices here, are there? Is it going to kick in this production function? No, again, there's no prices there. The tax is a price, so we want to look where there's prices. Is it going to kick in the final good producer's production function or profit maximization function? No, because they're buying, final good producer isn't buying energy. So where is it going to kick in? It's going to kick in here in the cost function, or we kind of derived this from the profit maximization function of the producers of the resource intensive or energy intensive good, didn't we? So it's going to kick in here. The price of energy, here it's WR, but we could say it's WR 1 plus torr, couldn't we? And basically, this is the only place in our fundamental equations where WR crops up. So instead of WR, we can write WR plus torr. So then we would have, WR 1 plus torr. So then you're going to have a 1 plus torr here in the end, when everything's played out. And again, going with Cobb-Douglas, power 1 here, that is going to reduce energy use, isn't it? It's going to have a significant effect on energy demand. If you raise the tax, if you make torr 0.1, so you're raising the price by 10%, you're going to reduce energy use by 10%, for instance. It's going to be quite a big response to taxing energy. That is the end of the substitution effects model.